Now is you're generating your strategies this week, and next week you're going to be generating your concepts. And this is a critical time in the semester. You're really setting your trajectory for the entire semester. Now I want to point that out in relationship to the timeline of the rest of the semester. So right now we're in week 3 doing the structures lecture, and you only have these 3 weeks or so to design and build and demo your most critical module. So time is tight. You want to be in the lab. You want to be prototyping things, bench level prototyping, quick and dirty, really getting a feel for the competition, right? You want to be in the lab. You want to be building those skills so you can make and demo that most critical module before we go to spring break. Now just to remind you again, these words that we use in the design process, a strategy is a set of actions or tasks or plan. It's your game plan independent of a physical embodiment, what you're going to do in the competition. So I want to see in your notebooks when we collect them next week all these different scenarios of actions you could do in the competition, what points you would score with those actions, what relevant physics are at play. All those are on the strategic level. Then we'll go into the concept phase, and you'll start describing physical embodiments of the machines that can accomplish your strategy. I talk a lot about this in what would have been last week's Thursday lecture. So you can find that online, and I go way into this. And then your most critical module is going to be that part of your robot that is critical to your strategy. It's going to be part of your concept, a module of your concept that you're going to make and demo to ensure that your strategy is viable. Okay? So just to reflect a little bit on what goes into an MCM, all of you are making your mini-me's this week. And this is a video of Orr Oppenheimer, who was a student last year, driving her mini-me. And like you have this year pushing a stormtrooper into the trash trench, they last year had to push a tea bag off the HMS Beaver into the harbor. So here's Orr trying to drive her mini-me. Whoops, it's stuck. It's stuck again. She's trying to get it to move. And the reason we do these exercises is that look at all these actions happening that you could never model in CAD, it'd be really hard to put an equation to, but you're learning it by driving on the game board. We want you to understand how it is to drive on the game board, how it is to climb the ramp, how it is to push something, right? Also, how fast you can drive. So again, this was a point scoring strategy last year, pushing that beanbag in. Look how fast that robot is. Look how long it takes to orient the robot to the beanbag and then get it in the harbor. Right? You only have 90 seconds in the competition of manual control and a full 2 minutes of total competition time. So you have 30 seconds of autonomous. Right? This is close to a minute-long video to score just a couple points. So this week, when you make your mini-me, yay, there she is. When you make your mini-me, you can do some time runs. See how long it takes to drive from the starting box to the ramp, or the starting box to the trash trench. And that can go into your analysis of your strategy, of what your robot could do. It also may make you think, boy, I might want to use more powerful motors so I can go faster. Okay, so then after spring break, what's going to happen is we'll really dive in to the hardcore robot design and build phase of the class. You will have 5 weeks between spring break and the competition. And that's when, in earnest, you're going to compile your modules into your whole robot. You may iterate it a few times. Hopefully you get a lot of practice. And then we'll do the competition on May 10th and 11th. Another point here is don't design in a vacuum. Be thinking downstream of the actions you're going to take in your design. Look at the course calendar, look what's coming up. We're posting milestones in advance so you can check those out. If you have a brilliant idea for a concept this week, sketch it out in your notebook. That's great. Still do your strategies, but it doesn't mean you can't come up with good concept ideas. Document everything. Okay, so now let's start the lecture. The first thing I want you guys to do is look at those materials. And just start bending them a little bit, but don't permanently bend them, and see how they feel, right? And I want you to get a sense of how they feel when you bend them. So you have 3 materials here. You have the aluminum with the line. We have the aluminum with the dot, or some of yours are blank. And we have the plastic. Okay. So, first, I want us to rank stiffness. So, in order, like I want you to just bend it. Don't permanently bend anything. Who thinks the line, the aluminum with the line, is the stiffest? So, okay. Who thinks the aluminum with the dot or nothing on it is stiffest? So it's about 50-50. Okay. Anybody think that the plastic is the stiffest? Okay, we got a joker, but he took his hand down really quick. So I'm gonna kind of rank these both tied at 1, and the plastic is like at 3. Okay, now I want you to think about strength. And strength is defined as how much you can load something until it bends or breaks. So I want you to play with these materials and just start slowly. Put a little bit of bending moment in. See how they feel until they start permanently bending a little bit. Right? And get a feel for this. This lecture is all about connecting theory of structures with feel of what's actually going on in the structures. Okay. So feel all of them. All right. So now, let's rank these again. Who thinks the aluminum with the line is the strongest? Oh, it's okay. You put your hand up. Okay, a few people. Who thinks the aluminum with the blank or the dot is the strongest? Okay, a lot of people. Anybody think the plastic's the strongest? No. Okay, this is the clear winner. Does anybody think the plastic is stronger than the aluminum with the line? You do? Okay. But how many people think the aluminum with the line is stronger than the plastic? Okay, by majority then, this is 2, this is 3. All right. So, that starts us off. And this is nice. You have some intuition now about these materials. Now we're going to go into the rest of the story. Yeah, do you have a question?
I have a question on how you define strength.
So if you take these materials, like the aluminums, you can bend them a little bit until they permanently bend a little bit, right? And so what I'm asking you to evaluate strength on is how much moment you can put in until they permanently bend, right? So I can play with that one. I can play with this one and bend it. And they should feel a little different. And we're going to go into what that feel actually means right now. So this is going to be a bit of a trip down memory lane all the way back to 2001. This could be a nice memory or a nightmare, I don't know, depending on your experience. But we're going to go back to 001 fundamentals and then reflect on what do they mean to us in machine design. So the first thing we're going to talk about is shear and moment diagrams. And I will post notes on this, but I suggest you also take notes, because you might make notes on stuff that I talk about that I didn't put up on the board. Okay, so first, let's talk about our sign conventions. Sign conventions. So a positive shear, if you have a little element of material, a positive shear is defined as rotating that little element clockwise, right? And a positive, so this is positive shear. And then a positive moment, I think the positive moment's a little easier to remember. It makes you smile. So it would bend the beam into a smiley shape. So that's a positive moment. Okay. And going way back to our fundamentals, let's just think about a simply supported beam with a force in the middle, right? And on one end, we have this little triangular support, which is a pin joint and locked to the ground. And at the other end, we always put a little triangular support on rollers, so that thing can move back and forth as the beam bends. And there you go, supported it. And I'm going to say that this force is occurring at a length of L over 2, and the total beam length is a length L. Okay? So, at the end of this lecture, and after you finish this course, I want you to think like, maybe I should tattoo backwards on my head, do a free body diagram whenever in doubt. Like, I want you to leave this course thinking like, God, Professor Winter harped on those free body diagrams all the time. But if that makes you think of doing free body diagrams, you're going to be like a million times better engineer than a lot of your peers. So let's draw a free body diagram on this bad boy. So here's our beam. And we just want the forces acting on this beam. So we have F here, and we have reaction forces, R1, R2, right? And as you remember from 001, you can sum forces in Y equals 0, because this is a static situation. So that's negative F plus R1 plus R2 equals 0. And then you can sum moments, and we typically sum moments in the counterclockwise direction as positive. And we can sum moments about, let's say, 0.1, R1. That's going to equal 0. And so we get F times L over 2 plus R2 times L. And that gives us R2 is equal to F over 2 is equal to R1. Right? That probably seems pretty comfortable for folks. You've probably seen that more times than you want to remember in 2001. All right, so let's go on and think a bit more about what this means. I'm going to unclip my sheets. So, something that you're going to want to do as an engineer is to be able to find internal forces in moments going on in this beam, because we want to know like stresses and strains and the actual loading inside of the beam. So let's talk about internal moments and forces. So, the rallying cry of this class is, when in doubt, do a free body diagram. So we could take a section of this beam, right, that we cut at some arbitrary distance x. We already figured out we can draw a free body diagram of the beam at this point. So we know that we have F over 2 acting right here. We know we have some sort of moment potentially in the beam, M. And we know we have some sort of shear acting in that beam, V, right? So again, what can you do to solve this? Figure out what these are. Where's your rallying cry? The free body diagram. And I know this seems like routine and elementary, but just wait. Like this is great stuff, and it'll all come together in a wonderful way. So you can do a free body diagram. I'll just do it right here. So in this case, we have sum of forces in Y again equals 0 equals F over 2 minus your shear equals 0. And that then gives you your shear is equal to positive F over 2. We have our sum of our moments equals 0. And we can again do it about that 0.1. And again, our nomenclature is counterclockwise as positive. And so that equals M minus Vx. And so then our moment is equal to Vx, which is equal to f over 2x. Now, something I want you to note here is that the slope of our moment is our shear. Another thing you may want to consider tattooing backwards on your forehead to never forget, because that's a good rule of thumb. Then you might say, and let's just put that down, dm over dx is equal to your shear. Awesome. And then you might say to yourself, ooh, what if we want to do a free body diagram of a section of the beam to the right of where we're applying the load? Right? So in this condition, so we have F over 2 here. We have our force acting at a distance of L over 2. And we have this arbitrary distance x. And we can draw still our positive moment conventions, positive shear conventions. And we can again sum this up. So sum of the forces in y is equal to 0, equals f over 2 minus f minus v. And so our shear is then equal to negative f over 2. So aha, it's flipped signs, right? And then we can again sum our moments about 1. And they're going to be 0. So that's negative FL over 2 plus m minus Vx. And so then our moment is equal to FL over 2 plus Vx. Cool. And so actually that should be, is that negative? No, that's right. These are both negative. Cool. All right. So let's put all these together. Actually, I want to keep that one in the middle so you can see it in reference. I hate this thing. I'm terrible at managing that board speed. All right, so now let's put all this together. Okay, so what's the slope in that second case? What should the slope of our moment curve be in the second case? Did I screw that up? So let's see. Our shear. Oh, so this is actually negative, right? This is a negative value. So this, again, is our slope. So our moment is going to go up and then down, right? That's the intuition I want you to have. But yeah, you plug the actual values in and the signs do work out. Okay, so let's go back to our free body diagram that we did here, right? Where this was, again, L over 2. Okay, so if we do a shear and moment diagram, we just figured out that for shear, in the beginning, we have a value of F over 2. And then we get to the middle, and it drops down to a negative F over 2. Boink, like that, and then up. So this is F over 2, and this is negative F over 2. All right, and then moment. And a lot of times, you know what's great about knowing these relationships, that the slope of the moment is the shear? You can just say to yourself, you know, even if you hadn't figured out moment yet, you say, all right, I know that at the ends of the beam there's no moment because there's a pin condition. I know the slope before and after the middle point. So I know it goes up and it goes down. And then you can plug into your moment equations to figure out that the max moment is FL over 4. All right, So does that seem pretty, routine? You guys have all seen this, right? Took this in double one. This is old hat. Okay. So now, whoops, that's the moment. So now let's talk about bending stiffness and stress. And what all that means. So bending stress and stiffness. Okay. And the next thing you may consider tattooing backwards on your forehead is how to solve any statics problem, any solid mechanics problem, by remembering three things. So every solid mechanics problem is solved by, one, your constitutive equation. And what that does is relates stress, an applied load, to strain, a deformation. Right? The second is kinematics. As engineers, you might want to know when you load something, how far is it going to move? Like your robot arm, is it going to flop all over the place? Right? So you want to be able to relate how much deformation you're getting in a structure, delta, with the strain in the structure, which is the kind of unit deformation. Right? And then the third, which you probably already know because you have it tattooed backwards on your forehead, is equilibrium, which is just sum of forces is 0 in a static problem. And so sum of forces equals 0. And if you're talking about forces per unit area, talking about stress. And it's how stress balances out forces. So let's now consider an example of a beam like you just played with under a pure moment. So here's your beam. You were just bending. You were putting, I don't know if you're putting a positive or negative moment into it, but depends on how you're feeling today. So we have a moment on each side. What's the sum of moments on this beam? 0. Sum of moments equals 0. Yeah, so that moment is the same on either side. So now, our constitutive behavior, we can write that as this guy, which you probably remember from 001, stress equals what times the strain? What relates stress and strain for a bending beam, for a metal, for anything? Modulus of elasticity, I love it. E. Excellent. Yep, and when you guys were doing your stiffness tests over here, you weren't plastically deforming the beam. So you were operating on the stress-strain plot in the linear region, right? Below the yield stress. So this has a slope of E, and then, after yield, it'll do something like that. Okay, so that's pretty straightforward. Now let's go to equation 2, which is a little trickier. So in the kinematics, you started with a straight beam, and then you bent the beam into an arc, like this. And let's say, and I think you probably remember, but you'll prove this in a second, that when you put a pure moment on a beam, you can bend it into a constant bend radius, which you often denote as Q, or rho, sorry. Right? So let's say there's our beam, and if we look at the edges of the beam, we bent it through an angle theta. Right? And let's call the original length of the beam L. So I'm going to just draw an arrow here. This is L. Okay. So thinking back to 001, what happens to the top of the beam versus the bottom of the beam versus the center of the beam in terms of its length? What's going on in the top of the beam? Yeah. Yeah, it's getting compressed. Nice. Compress. And then what about the bottom? Tension. Cool. All right. And so what does that mean lengthwise? Shorter, longer, right? So we can write that out. So originally the length of the beam, L naught, is going to be our bend radius times theta. And look, I define this bend radius down to the neutral axis, right? And so the middle of the beam isn't changing length. And then if I put a little coordinate system right here, so here's y, here's x. As I go further in the radial direction, what's going to happen? Beam length changes, right? So the final length of the beam, L final, is going to be that bend radius minus y times theta. Now why is it minus? If you go positive y, does that section of the beam get shorter or longer? Shorter. That's why it's minus. Okay, and then you can calculate the strain in the beam. And if you remember that strain is equated to your final length minus your initial length over your initial length. And this makes it unitless. This is like the stretch or compression per unit length, right? That's what strain means. So we can plug our equation in from up here. So we have rho minus y times theta minus rho times theta over rho times theta. Thetas drop out, and bam, you're left with an equation for strain, which is negative y over rho. Now, is this bringing back memories? How is this going down memory lane? Is this bringing back like night tremors? Or is this being like, oh, I remember this. This all looks familiar. All right, so we've got, can I do it while it's moving? Yes. So we've got two of our equations. We got 1 and 2. We've got constitutive and we've got kinematics. See, we're relating how strain actually corresponds to our movement, our deflection. So the last one is equilibrium. And this is the trickiest one to derive. So we can take our skills that we learned over here of cutting a beam at any arbitrary point. We're going to do that with our beam. So we'll cut it at this point. It has a moment on one side. Now what's going on in the middle of the beam to counteract that moment? That beam's not just spinning off into space in this free body diagram. Remember, like you can take a cut of any static object and sum the forces and moments, and they need to be static. So what is counteracting this moment right here? What? Speak up. The internal bending stress. So you know from here, you have compression up here, tension down there. So you can draw that as a stress profile where you have compression on the top and tension on the bottom. So here's compression, and there's tension. Now looking at that in 2D, or sorry, 3D, you can draw a 3D, here's a 3D cross-section of the beam. So the beam's going off in this direction, right? And we've got our moment acting like this. We can look at what's going on in this cross-section. Here's the neutral axis. And we can look